Okay. Okay, so today I said we're going to be doing something pretty complicated. Matrix representations. Of linear transformations. Yeah, the doctor also insisted that I sort of improve my posture. So if you see me sort of standing abnormally straight, then it's because, not that I feel like pretty cocky about myself, but rather the doctor told me to.
Power poses.
Basically, yeah. Yeah, it's like stick your chest out, sort of like keep your back a little bit curved. I don't like it.
Good for your mental and health.
I guess so. But you see, I don't believe in that stuff. So, like, morally, I refuse that stuff. I'm forced into it by my body. Yeah, actually, in martial arts, that's actually what they teach you, right? To stand, like really straight up, your chest out, to apply force better. It's like that's the better structure. But I've always hated that, and so I always do my martial arts sort of like as sort of as laid back as possible. But yeah, now my body has betrayed me, or I betrayed my body. Okay, so matrix representations of linear transformations. People tend to find this tricky. I'll try to explain it as simply as possible. So let us first recall an important fact that if linear transformations agree on a basis, then they agree everywhere. Right? That should be sort of striking, right? That all you have to do is, if the linear transformations have the same values on a basis, then they have the same values for every vector in the space. Right? That may seem sort of striking, but in fact it's just a consequence of linearity. Right? Linearity is a very constraining condition. Okay. Second thing I'd like you to recall is that given any matrix A in an n by m matrix, then we have a corresponding linear transformation T sub A, and T sub A goes from Rm into Rn, and it's given by V gets mapped to A sub A of V. Right? So, right, T is the map that takes V to just T sub A is a linear transformation that takes a vector and then multiplies that on the left by this matrix. It takes a vector, you give it a vector, and says, okay, I'm going to multiply it on the left by this matrix. Right? As you see, it takes an M. Right? V is in Rm. Right? And you have an n by m matrix, and that takes something in Rm and gives you something in Rn. Right? So that gives you a linear transformation from Rn into Rn. I should say that we often conflate A and T sub A. Right. So like if I'm talking about A as if it were a linear transformation, I'm really thinking about T sub A. If I say, oh yeah, A is a map from here to here, it's really T sub A. But anyway, it's basically the same thing. Yeah.
Does conflate mean like mix them up?
Yeah. Okay. Like I'm not gonna. That is, I sort of am gonna call these two. I'm gonna. I'll I'll treat A as if it were a linear transformation when in fact it's just a matrix. And when I do, you should think, oh, he's conflating it with T sub A. Okay. Okay. So given any matrix, there's a linear transformation that corresponds to that matrix. And what we're going to see is something sort of nice. That so we'll see something simple first. That if you have any linear transformation from Rn into Rm, then there exists a matrix. An n by m, that's an n by n matrix, such that T is T sub A. Is it clear what I'm saying here? Is it clear what I'm saying here? That somebody gives you an arbitrary, right? Over here, you have a matrix, and to the matrix, you get this, from the matrix, you get a linear transformation. Now we're going to say the opposite is also true. Given any linear transformation, in fact, that linear transformation arises as some matrix, right? As left multiplication by some matrix. Okay. So, I mean, this is just some arbitrary linear transformation, right? Right. You have some linear transformation, and then turns out that there'll be some matrix, so that the linear transformation associated with that matrix is our linear transformation. Okay. Okay. So. Let me give an example just to make sure it's clear. So here we have a map, say, from R3 to R3. Okay, and here it is. T of x1, x2, x3 is x1 plus x2, x1 plus x2 plus x3. This is a linear transformation, right? This is a linear transformation. And lo and behold, it turns out that T is the same thing as T sub 1, 0, 0, 1, 1, 0, 1, 1, 1. Right? Because if I take x1, x2, x3, and I multiply it by, if I left multiply it by this matrix, then I get, well, x1 plus x2, x1 plus x2 plus x3. Okay. So this linear transformation, which from the beginning didn't necessarily seem to come from a matrix, actually can be realized as left multiplication by some matrix. Okay, and what we're saying is that always happens. No matter what linear transformation you start off with, there's always going to be some matrix realizing it.
Even like the derivative?
Even like the derivative? Well, okay. So this is, right now, this is just from Rn into Rm. Okay, so the derivative is from Pn into Pn minus 1.
Oh, okay.
Okay, so right now we're just doing it on Euclidean spaces, but we'll see actually that something can be said for it's not exactly the same thing. It's actually more complicated, but something very almost exactly like this can be said. Okay, for a map between abstract vector spaces. Okay. Okay. So now I'm going to change this back to the notation that I have in the notes. Okay. 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 So how do we find the matrix? Here's the trick. Let E1 to En denote the standard basis in Rn, as always. Let this denote the standard basis in Rn, right? So E1 is the column vector 1 0 0 0 0. E2 is 0 1 0 0 0 0 0 0. En is 0 0 0 0 0 0 0 1. Okay. Okay. Let define, or let's just let, I guess, let A sub I be T of E sub I. Okay. So for each, see what happens to each standard basis vector as you map it through T. Right? That's in Rn, so these guys are going to be column vectors in Rm. Right? Right? These guys are in Rm, right? And there are n of them. Right? And let A be A1 to AN. Right? This is an m by n matrix. Right? So these guys are the columns, right? These guys are the columns. A1 is the first column, A2 is the second column, AN is the last column. Okay? Okay. So T sub A is T. T sub A turns out to be T. So I claim that this is the matrix that we're looking for. Just take T's action on the standard basis vectors, look at those outputs, and make a matrix out of those guys. And that's gonna work. Okay, and the reason is why? If we look at T sub A on the ith standard basis vector, right? This is an m by n matrix. So look at T's behavior on E. Let's look at T's behavior on E1. What do you get? T A
A1.
E1.
A1.
You get A1, right? Right. This is going to be A E1, right? A1 0 0 0 0. That's to say the first column, right? That will pick off the first column, right? And similarly, right? If I do it for EI, it's going to pick off the ith column. Right? So what's good about that? TAEI is AI, and TEI was AI. Right? In other words, both TA and T, recall that TEI, by construction, AI was TEI, right? So what does that tell us? That TA and T both agree on they agree on the EIs, right? So TAEI equals TEI for all I. In other words, you've got two transformations that agree on a basis, and so they're identical. So TA is T, or I should write it together. T is T. Okay, so the question was, can we find a matrix? Can we find a matrix that does the same thing as this guy? Right? Somebody gives you a transformation. Can we find a matrix that behaves the same way as the linear transformation that's been given to you? And you make the matrix. You say, okay, well, look, if I make a matrix by looking at T's action on the standard basis and taking those guys as my columns of my matrix, well, then that matrix will act on the standard basis vectors in exactly the same way that T acted on the standard basis vectors. And so I've got the matrix representation of T. Okay? So this gives you a matrix that does exactly what T does. Right? Okay. Like here, for example, how did we come up with this thing? What you do is you say take T of, right? You need to take T of 1, 0, 0. You need to take T of 0, 1, 0. You need to take T of 0, 0, 1. Right? The standard basis vectors. Right? And you put those things in a matrix. Right? T of 1, 1, 0, 0 is 1, 1, 1. 1, 1, 1. T of 0, 1, 0 is 0, 1, 1. T of 0, 0, 1 is 0, 0, 1. So I take those guys as my columns, and that's the matrix that does exactly the same thing, that acts on the standard basis and thus on everything in the same way that T does. Right? Right. T of the right. Right. T of E1 is 1, 1, 1. T of E2 is 0, 1, 1. T of E3 is 0, 0, 1. So I use those things. Those are my A's, right? Those are the columns of the matrix that that represents this linear transformation. Any questions? Ask now, because it's only going to get more complicated. Ask questions. Right? Anybody confused at any point? Right? At what step are you confused? Andrew?
Just what you just wrote with E1.
Yeah.
Isn't E1 equal to like 1, 0, 0?
Yeah.
So if you take T of E1, wouldn't it be 1, 0, 0 instead of 1, 1, 1?
No, T of 1, 0, 0 is going to be, right? If I remember what T does. T takes x1, x2, x3 to this. So T of 1, 0, 0 is going to give me x1 plus x2, x1 plus x2 plus x3. 1, 1, 1. Okay. T of 0, 1, 0, right? T of 0, 1, 0 is going to give me x1 plus x2, x1 plus x2 plus x3. Right, 0, 1, 1. Okay. Yeah, Mia.
Is that how you find A for every linear?
Yes.
Okay.
Yes. Right? So
And A is the
matrix representation of this
the-
linear transformation.
okay.
Yeah, so you have a linear transformation, and it turns out that the linear transformation can be realized as left multiplication by some matrix. Right? Here's a linear transformation. Turns out that you can find a matrix that acts on the space just like your linear transformation did. Okay. And here's how you do it. Right? You look at how the transformation behaves on the standard basis vectors, and you put those things into a matrix, and that matrix is what you're looking for. Yeah.
So you always use E1, E2?
Yeah. Yeah.
Okay.
Yeah. Yeah. Teresa.
Can you explain the step from, so I understand the bottom part with the AX, but can you explain how you put that into TE1, TE2, TE3?
Right. This thing is TE1, TE2, TE3.
Right.
Right? TE1 is 1, 1, 1.
Right. Okay. I get, okay. I guess it's the transpose that is.
The transpose. What, you mean you're taking the transpose of this matrix, or?
Well, if you like look at, yeah, I think I'm thinking about multiplication the right way.
right? So right, you multiply 1, 0, 0, you get x1 plus nothing. Here, right? When you multiply these guys, what do you get? You get x1 plus 1x1 plus 0x2 plus 0x3.
Right.
Right, that's x1. You get x1 plus x2 plus nothing.
Yeah.
x1 plus x2 plus x3.
Right. How did you put it up to TE1? You just took the rows, or you took the columns.
So let me go back like this. Okay. So we have this theorem, and the theorem says that if you have a linear transformation, then you can. It turns out that there's some matrix that does exactly the same thing. Okay, and you can find that matrix by taking your linear transformation and acting on the standard basis vectors, and then putting the results in a matrix.
Right.
Okay. So here's my linear transformation. I'm like, what matrix does it correspond to? So I say, okay, well, the theorem that we just worked out says that you need to look at T's behavior on E1, E2, and E3, and then put those things as the columns of some matrix. Okay? You say, okay, so what's TE1? TE1 is 1, 0, 0, right?
Yes.
That is to say, 1, 1, 1. Right? Here's the description of T's behavior. T takes in x1, x2, x3, and returns x1, x1 plus x2, x1 plus x2 plus x3.
Right.
X1 plus
yeah,
x2,
yes.
x1 plus x2 plus x3.
Yes.
Okay. T of 0, 1, 0, right, is going to be what?
It's going to be T times, so it's going to be 0 times x1 plus 1 times x2 plus I.
This is x1, this is x2, x3.
So it's
So it means
x2.
0, and then x1 plus x2, 1. x1 plus x1, this is going to be x1 plus x2 plus x3, that's 1.
Okay.
Okay. T of 0, 1, 1, 0, 0, 1 is 1. Well, this is your x1, this is your x2, x3. You're going to get back x1,
Right.
0, x1 plus x2, 0, x1 plus x2 plus x3. 1.
0.
What? 1. Right? And so these are going to be the thing we just worked out says put those things in a matrix. And that is the matrix which behaves exactly the same way as T does.
Okay.
Okay? Yeah, Mia.
I'm just confused. I understand most of it. I just don't understand the n by n. So A is an n by m
It's-
matrix,
It's an m by n, yeah.
and you multiply A times a n.
Yeah, an n by 1. Yeah.
N by 1 matrix, and you get an m by 1
Exactly.
matrix.
Yeah. Right. Right. A, you multiply. If you feed it an n by 1 in n by 1, it gives you an m by 1. Just like, right? T, you feed it an n by 1, and it gives you an m by 1. Yeah.
So if A is A1 through AN,
Mhm.
that's an m by n matrix.
Yeah.
But each A is m by 1.
That's right.
Okay.
Yeah.
So when A equals T of E,
Mhm.
that is an m by 1.
That's right. That's right.
Okay.
That's right. Each of these things is the output of T, is an output of T, right? Right. The outputs of T are all m by 1. The outputs of T are all m by 1. Okay. Okay. So, right. So the moral is, given a linear transformation, you can find a matrix that does it. Okay. So so for example,
I'm sorry, is
Yeah.
n, that's an m by n matrix, where m is the number of
yes,
rows?
yes.
Okay.
Yeah. Okay. 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 Let's do one more example. Say. Okay, a simple, easy example. Projection onto the x-axis. Okay, so here's your linear transformation. It projects onto the x-axis. Okay, so t of xy is x0. Okay, tell me what the matrix work out the matrix representation. While I strike power poses in front of you. No, I'll go outside. Okay, so what is it? What is it? What do we need to do? Teresa, I'll make you do it, okay?
Okay.
Right. So what do you do?
So you do the standard
Mhm.
basis.
So what's t of 1, 0?
See, that was the part where I pretended like I knew what you were telling me, but I
That's
just
it.
wanted.
I thought so.
I think you realized that.
Of course. Okay, so look, t of 1, 0, right? T takes xy to x0.
Right.
So t is going to take 1, 0 to 1, 0.
Okay.
Okay. Now t takes 0, 1. T takes xy to x0.
Right.
T takes 0, 1 to
0,
0,
0.
0. Mhm. Right? Okay.
Okay. Yeah.
And that's going to be that is our matrix. That's our matrix, and you see it actually does behave the same way, right? Because 1, 0, 0, 0. If I hit xy with it, what do I get? I get 1x plus 0y, right? Right.
Yeah.
1x plus 0y, and then I get 0x plus 0y. So this matrix does behave exactly as the transformation. Yeah, Mia.
Do you know how many t's to do?
Well, you have to do the whole standard basis, right? We're in R2, so there's two elements of the basis.
So if you're in R3, you just do 3.
Yeah, right, because you have to do the full standard basis.
Is it?
Right, so see, if you're going on Rn, then you have the standard basis E1 through En, and you use those guys.
Okay.
Okay, that will give you, right, n columns,
Mhm.
right, and the outputs will be m dimensional. Yeah, there'll be m, so m rows. Right, but more importantly, you have to have, you're trying to create something that agrees with t on the standard basis, right? Remember, that's the game. We have these two things, and they agree on the standard basis, and so they agree everywhere, right? And so we created something. This matrix agrees with t on the standard basis, and it agrees with t everywhere, right? Right. Why does it agree with t on the standard basis? Well, because we made it so that it would, right? When we look at this matrix behavior on the standard basis, what do we get? We get the first column and the second column, which is what we chose it to be.
Yeah.
Okay, Okay, let's go on to the more complicated things. Okay, so here we go. Okay, so matrix representations of linear transformations between abstract vector spaces. Okay, so what we saw just now was for matrix representations of transformations on Euclidean spaces, and now it's just vector spaces. Okay, so here we go. This is a little bit tricky. Before we do it, I need to say something. From last time, I forgot to mention the following theorem. T is an isomorphism. So you've got T from one vector space into another. Okay. T is an isomorphism if and only if there exists a linear transformation. Let me say it this way, sorry. Let me give a definition first. Sorry. Definition. Suppose you have some linear transformation from V to W, a linear transformation. If there exists another linear transformation S going in the opposite direction such that T followed by S is the identity on V, and S followed by T is the identity on W, then we say T is invertible. Right. Is an invertible transformation. And call S T inverse. Yeah, Haley.
So are you saying that when you say S or T followed by S,
Mhm.
and that's like the S
Composed with, yeah.
T, so are you saying you do the transformation and then you do
Yeah,
S?
yeah. So you got one vector space, you've got another vector space. T goes this way, S goes this way.
Yeah.
So if you start off with some vector here,
Mhm.
and it turns out that you run it through T and then you run it back through S and you end up where you started.
Mhm.
And similarly, whenever you start off with something in here, you run it through S first, you run it back through T, and you end up where you started. Right? If that happens all the time, then these guys are inverses of each other. Then we say the matrix. Then we say the transformation is invertible.
So by identity of V, or what is that?
By that I mean that nothing happens.
Okay.
Right? That is, you could just as well write it like this: S TV equals V. T
Mhm.
TSW equals W for all V in V, for all W in W. Same thing.
Okay.
Yeah. First, Eleanor, did you have a question?
Yeah, I'm not sure where I'm getting this wrong, but to me it looks like the identity stuff is flipped because
Oh, did I write the wrong way? Let's see. T goes first, T and then through S. No, it's right.
well,
Yeah.
so isn't you start with V and then you go through T and then you go through S, you end up with V again.
Yeah, you come back to V.
So then
the identity transformation on V.
So right, so isn't that T and then S?
Yeah. Yeah, so T happens first and then S happens.
Oh, okay.
The order is like T happens first, and then S.
Okay.
Yeah, it's a little confusing, but that's it's just like functions composition, right? If I write f composed with g, I mean
Oh,
f
okay.
of g of x. It's identical to that. Teresa.
What do you mean by the identity of the?
That nothing happens. That
Okay.
nothing happens. So
Okay.
the transformation that does nothing to elements of V.
Okay.
Yeah, if you don't like that, then just think here,
Okay.
right? That if you do T and then you do S, nothing happens, right? In other words, ST is the identity transformation. ST is the identity transformation on V. TS is the identity transformation on W. Yeah, really, Elena, one doesn't put the composition here. One just writes it like this. Yeah. Just thought it might be helpful. Okay, so transformations, invertible transformations. For example, we've done this a couple of times. You have some vector space, and then you have it's an n-dimensional space, and you have some basis, right? B1 through Bn. Right. If you start with a vector here, V, you can map it down to V sub B, right? The coordinate vector with respect to the B basis. Right? I hope you all remember this. It's crucial. Right? Right. You have some vector space, you have some basis, and that gives you a map from V to Euclidean space. Right? Namely, right, you map down to the coefficients used in the unique linear combination that expresses V. Right? Right? This should be very familiar. Right? This is an invertible transformation. This turns out to be an invertible transformation. Right? If you start from here and go back up, then that will return you back to the same thing, right? Like, right. So, I'll write it sideways. Right. So here's your V, right? And suppose that V has some basis, B, right? B1 to Bn. You remember how to get the coordinate vector, right? Somebody gives you a vector here. What do? You express it as C1 B1 plus Cn Bn, right? And then the coordinate vector of V with respect to the B basis is just those coefficients, right? Right? This is the coordinate vector expression. Okay, and what's going to be the reverse? What's going to be the inverse transformation? Somebody gives you a bunch of coordinates here. What are you going to map back to? What will reverse the effect?
The basis.
Not the basis itself, but the
Inverse?
How do we get back to V? How do we get back to V? Here's V, and we map it to these coordinates. From the coordinates, how do we get back to V? It's simple. Just take V. Thank you. The linear combination, right? So if somebody gives you a bunch of things, just go back to C1 B1 plus Cn Bn, right? And then if you started off with some guy and went down to its coordinates, then from the coordinates you come back exactly to that guy, right? It should be simple. Not sure if is it simple. Everybody, close your eyes for a second. Anybody confused? Raise a finger, please. Okay, put your fingers down. Okay, open eyes. Okay, so I'll say it one more time. Right. You have a vector in a vector space, right? you have a vector space and a basis. I'm trying not to look at anybody who raised or indicated confusion. You have a vector space. You have a vector space and a basis, right? I'll just look at the board. That's it. You have a vector space and a basis, and right. Then we have this thing that we call the coordinate vector. The coordinate vector for that with respect to that basis, right? So you start off with the vector, and then that vector gets mapped. What happened?
A bird tried to fly in.
Oh, is it okay?
Good.
Okay.
It's still flying now.
Okay.
That's greatness.
Yeah, it's a
Okay. So right. You have a vector space, you have a basis. Given any vector, right, we had this way of mapping it to its coordinates, right? We had this thing called the coordinate vector with respect to that basis. What was that? That thing was a bunch of coefficients, which were the coefficients you got by expressing V in terms of the basis, right, as a linear combination. Right. Okay. So now, let's call that map T. Okay. Now we want a T inverse. What's T inverse going to be? It's going to be a map from Rn back to the vector space. It's going to take something in Rn and give you something back in the vector space. Well, what do we need to? How should it act? How should it act to undo what just happened? Well, it should go from here back to the corresponding linear combination. Right? It should go back to the corresponding linear combination, right? Because then, if you start from somebody and go to the coordinate vectors, you go from the coordinates back to the guy itself, right? So these things reverse each other. Okay, so these are inverses of each other. Okay, so this matrix, this transform. This is the transform, and this is its inverse. Okay. So there's a theorem that says that T is an isomorphism if and only if T is invertible. T is an isomorphism, that is, it's one-to-one and onto if and only if T is invertible. Okay. I'm not going to explain this theorem. It's not difficult, but I don't want to take the time to do it. Our goal is to talk about matrix representations between abstract vector spaces. Okay, so let me sort of sketch. We only have a couple minutes. We're not going to be able to do the whole thing. Let me sketch out what's happening so that I can sort of seed some ideas in your brains. Okay, so here's the theorem. Here's what we're going to see. You have V and W. So you have T between V and W. This is a linear transformation between vector spaces. Linear transformation between vector spaces. Then you have two bases, V1 through Vn and W1 through Wm bases for V and W respectively. Okay, so you have these two bases. Okay. Okay, so here's the picture you want to have in your head. T goes from V to W. T goes from V to W. Here we've got a basis for, we have a basis for V, we have a basis for W. Okay. Those bases give us the coordinate maps, right? We have a map that goes from V to Rn, we have a map that goes from W to Rm. Right? Namely, the maps that we were just talking about. Right? Going from the vector to the coefficients. Right? With respect to the E basis. Going from the vector to the coefficients with respect to the F basis. Okay. So we have these maps. I'm going to call them P and Q. Okay. What we're going to see is that there is a matrix A such that A of V E with respect to E equals T V F for all V in V. Okay. That is to say, if you start with a vector V here and take its coordinate vector with respect to E, and then hit it with A, then you get the same thing as if you took that same vector, ran it through T, and then took the coordinate vector with respect to F, took the coordinate vector with respect to F of that. Okay. And this thing, this A, is called the matrix representation. Okay. So for example, if you look at the differentiation operator from Pn to Pn minus 1, right? Here we've got this thing that maps it to Rn, we've got this thing that maps it to Rn minus 1. There will be some matrix that behaves like the differential operator. There will be some matrix that makes, what we say is, makes this diagram commute. That is, if you go this way or if you go this way, you get the same thing. There will be some matrix that behaves just like the differential operator in this sense. Yeah.
Is the matrix A in Rn, or is it?
Right.
Is
So
it's only it's like only numbers. It's not.
it'll be numbers. Yeah. It'll be numbers. It will be a n minus 1 by n matrix.
Okay.
Right. Because you're going from it. Right. You want to go from
n to n minus 1.
You're going from n to n minus 1. So you need this sort of matrix to do it.
Okay.
Okay. Okay. So there will be some matrix that encapsulates the behavior of the linear transformation in this sense. Okay. And we'll see how to find it.